I could go through the announcement slides if you guys would like.
We'd actually like if you didn't do that.
Alright, so I'm calling this a better sorting app. I'll see why in a second, but it's using Python and then a package called Pulp, which is a linear programming module basically. And we're going to be using it to create optimal subgroups from a group of individuals. You guys both know me, so this is less relevant, but you can look at the embarrassing picture nonetheless. But he's awesome. The one thing that may be of interest is just all this is basically on GitHub, so feel free to use it at your leisure. All good presentations begin with a story of some form. So as part of our work weekly ritual, we have Wednesday afternoons dedicated to like a learning session basically, so we call it 10x time, which is just kind of a catchy name. But we had this idea to, instead of having 10 people in a Slack video chat together every single time where you're always either talking over someone or the latency is too long where you don't feel like you can chime in, we thought, why don't we split off into these little subgroups, and each subgroup can like take a Coursera course, or they can work through a tutorial, like whatever the learning topic wants to be. So the first step of that process was everyone in the Slack chat put like a list of, here are the 6 topics that I'm really interested in, and you had to go through and vote with like a thumbs up, thumbs down if you were interested or not. And everyone had like their pet projects, right? So like I had an Elm tutorial that I really wanted to go through that no one else voted for at all, and there were a couple like that. And then there were quite a few in the middle where you'd have, 4 people out of the 10 or something that wanted to vote. And then a couple that were really popular, but as we got to talking about them, were not anyone's like first choice. They were just like the good compromise choice. And so once we'd gone through that process, we got to 10x time, and it wasn't clear, like, what do we do now? Like, how do we organize into these groups? And so this is actually a quote from my boss who said, maybe it's simplest to jump onto a quick call to organize into groups, and then you can see that like 17 minutes later the call ended, and we had finally assembled into these teams that were still probably not like super optimal. So my thought was there's probably a better way to do this, and then about a week later I saw this tutorial come through on using Pulp for LP problems, and I thought, okay, this is actually probably a pretty good test case for that. So I have no idea what everyone's like mathematical background is, so is it worth walking through a quick linear programming example?
Yes.
Okay. So Wikipedia definition here, but basically like an LP is just a way to find an optimal solution given a set of linear constraints and objectives. And so my simple example is if you imagine that we're like an evil lunch lady, and we get to determine what the meal plan is, subject to some constraints and desires here. So since we're evil, we want all the kids to get more than like 1,500 calories per meal, why not, per something. And we have 2 options. We can give them sugar or we can give them kale. And those are our only 2 options because we want to keep this plottable on a 2D graph. And we know that sugar has 200 calories per serving and kale has 75, and so we want the summation of those 2 to be greater than 1,500. While simultaneously we want the nutrition levels to be as low as possible, so we know that sugar doesn't have very much nutrition, so we're going to give it 10 units, whatever that should be, versus 100 for kale, which is way more nutritious. We also know that parents will get mad if you feed their kids 100% sugar, so we're just saying, like right from the get-go, parents say, you can only give my kid 5 units of sugar per meal, or I'm going to write you an angry letter. And with those constraints, we want to figure out what's the optimal blend of our 2 ingredients to minimize cost. If sugar costs $25 per serving and kale costs $100. And so since we only have 2 variables here, like we can do this visually, which is kind of nice because it frames up, we're going to step into way more variables here in a second, but you can at least kind of see how it works. So the calories is the blue line here, and this is just a relationship between kale and sugar on these 2 axes. And we want calories to be greater than the sum of those 2 things. So basically what this says is anything below this blue line doesn't meet our constraint. So we can just imagine kind of like cutting that piece of the page off. It doesn't exist anymore. Nutrition's the opposite way, so we're going to cut off everything above that because we don't want to give the kids too much nutrition. And so already we've kind of like isolated it to this little region here. And then the sugar constraint, that one's easy because it's just a vertical line right here. It's kind of hard to see on the grid lines on the screen, but that's really nice because then with the 3 of these, we've said basically like we have within this little shaded region to pick. And there's actually a theorem for the life of me cannot remember the name of, but like in a linear system like this, the optimal solution is going to sit at one of the endpoints. Basically, it's not along the slope of any of the lines. So in this example, we just pick those 3 points and test them manually. And as it turns out, I think it's this one. That's the optimal solution from a cost standpoint because we've said sugar is $25 and kale is $100. So basically, we want to give them like as little kale as possible. So that's the gist of it. We're going to extend that, obviously, into a much more complicated solutions here. So beforehand, we had sugar and kale as like our 2 variables, and they're basically continuous variables because anything above 0, like we could have theoretically given 1,000 units of kale or something, right? Here, we're trying to assign individuals into classes based on their stated preferences, which are the values here. And so instead of saying like, Anita has a value of 1,000 in microvenue, that doesn't make any sense. We're just going to use binary variables and say 0 is they're not in that class, 1 is they are in the class. And so what we'll end up with, and we'll define these here in a second within the Python code, is a binary variable for each of these cells within this entire table. So we end up with whatever that is, 10 times, I think those are 10 there, times 4, so 40 different binary variables representing nothing other than the person's membership in a corresponding class. The values here are, 1 is like the most desirable, and you can go 2, 3, some of these individuals only have 2, like right here, so they chose not to rank a 3rd one. If there's a blank cell, it indicates that they do not want to be in that class whatsoever, and we'll see how that kind of factors in here in a second because you have to do a little bit of a trick to get that to work. But similar to what I was describing, like we have one class that's a clear, like, happy medium for everyone. Everyone except one person has rated that a 2. And then we have 3 classes where some folks are pretty excited about it, but quite a few people don't want to be in it at all. So the problem we're trying to optimize here is trying to minimize for each of the people the sum across those rows we just looked at of their choice variable, so that's 0 or 1, times the cost, which in this case is just the rating that they applied to it. So kind of logically thinking through that, it would be a perfect outcome if everyone had only one class and it was their first choice, right? That would be the minimal outcome, assuming we want everyone in the class. We may or may not be able to get to that, just given how the problem's structured, but that would be the best outcome. So choice is the variable, cost is just a constant, so we're given that, we don't have to solve for it or anything. We do have 2 constraints. One is every person is in exactly one class. You can't take more than one, and you can't just like sit it out and not take any, because if we were minimizing it, would just say don't put anyone in any classes, and that would be very exciting. And then this one, which is actually like, in my mind, the coolest part of the code or the problem is we want to be able to specify a minimum when we run the code that says if you're going to have anyone in a class, it needs to be at least 2 people or at least 3 people. So you can't just have like one person from the team go take a course on their own. And the reason that's cool or interesting is we're solving linear programming, but we basically want a constraint that is okay at 0 and then takes this big hop, and it's okay at 2 again, but it's not okay at 1. So it's like discontinuous, which is a weird concept when you're thinking about just plotting something in a linear fashion. So there's a little trick to get around that. So we'll start digging through some code that we can actually see all that. I won't go line by line through all this. I'll just try to point out some interesting things. But Like I mentioned, this uses pulp, which is just an LP package. It has the ability to plug into different solvers from other packages. So like, it's not the case in a simple problem, but if you had a really complicated problem that was amenable to a certain solving technique, you could just like grab that technique from another package and then use the syntax and kind of the structure that's embedded in pulp to structure your problem, which is neat. I just used the default solver here because it doesn't matter for what. I set this in value. This is the blank cell, if you remember the data set. So if someone didn't rate a class 1, 2, or 3, we're basically saying it's a 10,000. And so what that's telling the optimizer is, like, basically under no circumstance should you ever put someone in a class that they haven't given a number to. And if you think about, it's trying to optimize little differences between like 1s and 2s, the idea that it could accidentally grab one that's going to put a 10,000 value into the problem means that it's never going to do that if there's any possible way that it can avoid it. So you could go about that a couple different ways. Like here I've set it very high. If you cared more about getting more people into their first choice and less about not putting someone in a class they really didn't want to be in, then like you could set that at 5 or something and it would be a more equal trade-off between those things. So it's this weird like unitless parameter that you have to just kind of set by feel based on the problem. So that's kind of neat. And that will come back into play when we calculate costs. Here, this is basically just like grabbing data. So it's set up as a command line tool, and then there's a corresponding, it's an Excel file here, one of my to-do items that I didn't get to use, a structure so I can take CSV to, just so it's flexible. But it's exactly the file that we looked at earlier. It reads that in with pandas and then does a little manipulation just to grab like the person names and the class names and the cost and things like that. So that's what raw data and really all of this section is doing. Prob, we'll see quite a few. This is just creating the class from the pulp package. So it's an LP problem. I've titled it here optimal 10x grouping because that was what I was looking at. And then we want to set an objective function to minimize the value, basically. And then the last thing on this page is just basically looking at all of the cost matrix, which is the rating values from the table we looked at earlier, and saying if there's a blank, which it's interpreting as an, then assign this 10,000 value into those. So just like some kind of cleanup. Defining the LP variable is actually really easy, which was a nice surprise here. I made a little name factory that just calls it choice, then I think it's the name of the person and then the name of the class in that order, INJ. So it's just a little helper function, but all we need to do to create all of those 40 variables is for each of the people, and then for each of the classes for each of those people, create an LP variable, which is a class from pulp, give it a name, and then tell pulp that it's a binary variable, and that's all we do on that one. We're also going to create some extra variables. Well, this is related to the little twist that I talked about earlier. We're going to create a variable that indicates if there is any membership in a class at all, regardless of if it's 1 person, 2 people, 10 people, whatever. It just is 0 if there are no people in it, and it's 1 if there is at least 1 individual in that. We haven't assigned values to any of these yet. We're just setting up the variables so we can populate them and mix it. And that's this has membership list. Next, we set up the constraints, and if you are interested in this, there's actually a really good Stack Exchange article about implementing Boolean logic structures in LP constraints, which took me a while to kind of wrap my head around why that's even a thing you would want to do. But you can implement AND or XOR, like all the basics, with binary variables, some of what we're kind of doing here, and it's pretty clever. Like, I was very impressed by it. I would not have thought of it on my own. So if you're interested, just look that up, but it's way more elegant than I would be about it. For our constraints, the first one's pretty simple. We're just going to say, and this I think is a good illustration of how like user-friendly pulp is. We're going to attach to the problem that we created earlier a constraint, just assigned to it with an addition, that the sum of each person's choices, each person's choice variables has to equal 1, which just says across all the different courses, each person has to have exactly one class that they have assigned a 1 value into. And that's the code that does it. It's simpler than I thought it would have been like from the outset, which was kind of cool finding. So we're doing that for each person, obviously. And just for clarity, this choices structure, it's a 2-dimensional array where the first subset is the person, and then once you access the person, it's just an array of the variables for each of the courses. So that's why this sum works. The next constraint's the tricky one. So we want to create or populate the has membership piece first. So if the sum of every choice for the alternative is 0, has membership must be 0, just because like no person has been assigned into that group yet. While simultaneously it's greater than or equal to the choice for each person within that alternative. So if any one person is a 1, this has to be greater than or equal to 1. If the sum of them is 0, so none of them are 1, then it has to equal 0. And that's how we kind of get that toggle for has membership between like just capturing if there's anyone at all in the group. So this one would, so sum of choices for everyone involved, it would be, like if everyone signed up for that course, it could be 10, that's fine. Like your 0 or 1 variable can be less than or equal to 10, that's okay. So all we want this line to do is capture the outcome where everyone said, no, I don't want to be in that class, and it's a 0. And then this one's capturing, did anyone say, yes, I want to be in the class? They're kind of like two sides of the same coin. But you need them both to toggle that on. And then the last one is again, kind of the coolest of the bunch. So if a group has any members, we want to enforce a minimum number. This args.min, it's a command line argument that we passed in. So the examples I think are run like 2, 4, and 5 that we'll see in a second. But you can set it to any arbitrary integer. And what we're going to do is say the sum of the choice variables for every person and class combination has to be equal to that constraint that you've passed in times the has membership variable for that class. So if there is anyone in the class, has membership is going to be a 1. You multiply that by the minimum number and say the class membership has to be greater than or equal to that number. If has membership is 0, then it's going to multiply your minimum times 0 and say it has to be greater than or equal to 0, and it's going to turn out to be 0. So that's the weird little toggle is over here that allows it to behave in kind of a non-linear way, which I don't know, I found that kind of neat. And then the last piece is, again, pretty simple. So this is where we actually tell it what to like calculate when it's trying to optimize. So all we're doing is taking each of those variables times the cost and then adding them all together and saying, hey, go minimize that, because that's how we set you up. And then run solve and display the outcome, which looks like this. Sorry about the nasty blue background, but I didn't realize it was there, and then I didn't want to go regenerate all of these. But this is what the outcome would look like. This is with a minimum like class count of 2, and so I set up some little variables here. Our optimization score is 100, and what I tried to capture was how close are we to getting everyone in the best possible class for them. And if you nailed it, like you got the best possible score, it's a 100, and if you we're as far away as you could possibly get from that without grabbing some of the 10,000 values that we arbitrarily assigned. It's a 0, and it's just proportional in between there. So we achieved a 10, which is the minimal value that can be achieved within these constraints that we talked about. Perfect is 10, so we got a 100 score. The worst possible outcome would have been a 25, and then here are the groupings. And not surprisingly, these are the 3 courses that we talked about earlier, like not being the compromise course. They're the ones that some people really liked and other people didn't like, and it's putting everyone in the right course for them. And that's with 2. If you change it to 3, it actually doesn't change at all because each of these courses already have 3 people, so that can provide a constraint. But if you change it to 4, it shifts it around quite a bit. So microbes in you, indoor beekeeping, and trial by wire are the 3 here, and then you switch to 4, and it grabbed a completely different course, which again is the compromise course that a lot of people were happy with. It switches a bunch of people into that because now it realizes, like, I can't put people into the groups that they really want because this minimum count of 4 has become too binding. And you see that really show up here because our optimization score dropped from 100 all the way down to 60 just by increasing the group size from 3 to 4. And so if I were in a business setting or something, I'd look at that and be like, okay, how important really is moving from 3 to 4? Because 3 is really good and 4 is like, yeah, not really that good at all. And so if a business owner or whatever wasn't really intent on there needing to be 4 people exactly for some reason, then you'd want to go with 3. If you bump it up one more to 5, it continues to drop, but it doesn't drop nearly as much. It's really that move from 3 to 4 that, so you move from 100 optimization score to 60, and then increasing it one more just moves you down to 53. So it's like you've kind of flattened out at that point. I don't think you could probably increase it. Well, you couldn't do it anymore because you only have 10 people. Your group size is 5 already, so it levels out at the end. That's the optimization. Yeah. Like I said, they're all up on. Yeah, if you're interested.
That's really interesting.
It was kind of neat. It was a good learning experience. And before I refactored it, it was written in like a very imperative style. The upside of which was the entire process was like that long on the screen. Like it was super short to write all this out because so much of the work's just like farmed out to the packages, whether it's pandas or NumPy or whatever you're using. So.
Yeah, that's a fun problem too.
Yeah.
Like, I'm thinking, I don't know quite when I would apply this, but I would enjoy the opportunity to.
It's a hard problem to phrase because like you don't want to talk about like splitting people into subgroups and like it sounds really negative, but it's like, well, people want to do the things that they have stated they want to go do. Like that would be
so you're reaching the sorting hat.
yeah. So that's sorting hat.